Welcome back to another CocoLabs video. This is Phase 2, which is self-driving. I am back at it with Ayush and Akil, and today this video is going to be a little bit longer as we have to get into some major systems that went into this robot. We are doing a distance test to see if we stand here, how far it will go before the RC loses signal, and then we may have to run after it. So, we are on the other side of the field, and there's a lot of grass here, and a bunch of it got on here, and then there's like this ugly stuff here. Oh shit, is that poo? Shit, that's poo. Once we were satisfied with our remote connection, we started working on endurance testing, seeing how far our robot can drive. We replaced our battery with a new battery called a LiPo, which stands for lithium polymer. This battery was smaller, but had a bigger punch, and it also was much lighter than the previous batteries that we had. The one downside was that it was actually far more dangerous than any of the previous batteries that we used for CocoLabs, and to decrease risk, Akil built housing for a battery.
Alright, so this is our amazing 3D printed battery mount that I made. Basically, it's meant to fit a 4S LiPo, so we got a 4S right here, which we're going to use in our robot. And there's two here because you can put two LiPos in, but for the whole use is just to keep them secure instead of like wobbling around in a metal area. So you just pop them in really easily, and then you can just plug it in right here, just like that. And to remove them, you just unplug it and just pull it out, and then you can go charge it.
Our battery could last pretty long, but our electronics and connections could not.
Oh, lights on.
Got it? Okay.
Maybe we should rage quit.
Reset.
Maybe we rage quit?
Nah, we got this.
We got this after like 3 hours of debugging.
We only got a few more resets and we'll be at software.
Yeah.
And then we can just push it to work again. Or we can
I think we're done for today.
Oh.
Oh! We got something.
Comms, we got comms. You got comms, buddy?
Comms.
Of course, comes
You have comms. Good.
You know, I love how this machine, it's like, not a break it apart, just to revive it.
Here, I'll give you a push.
No, don't.
How are you at rage quit?
What seemed like a journey, though in reality we've only probably traveled like 300 feet. Once we knew that our problem lay with the electronics and connections, Akil got to work building a small circuit board just to hold all of the small electronics together and keep it more compact and organized.
Alright, so this is the very crude PCB that was made. Basically, we have the remote control, goes through antennas to the receiver. Receiver goes Receiver goes over here, and then goes from here to over there, and then GPS goes to there, and then goes there. We have Arduino Mega for LiDAR, and then we have a regulator that reduces 12 volts to 5 volts to power everything. We have a little bus there, and then yeah.
Nevertheless, connection issues persisted.
There's a problem with the connection for SEL and STA to the actual chip. So here on a working board, you can actually check that it's working by going here, and then you could connect to the pin. There's continuity, you can actually hear it. But on this, if I hold it onto the wire, there is nothing. So any pin, there will be no connection, which means something was fried either in the chip or one of those traces. So, yeah. Now I have to gotta resolder that.
Akil redesigned the electronics board, making it much more robust than previously.
This is perf board with headers and board soldered on, so that in the case that something gets fried or we need to replace a board, you can just go like this and pop it out, get a new one, and then just pop it back in. Super easy to replace. And then on the other underside are traces and a few wires to basically just bring everything together, connect them. So just a lot better than this, because the only wires that are really sticking out are output wires. So output for LiDAR to the Robo Rio, and then power wires.
Even with this new model, connection issues still persisted. So, if you look on this Nano, there's a D8 and there's a D9 pin. And there's two red wires. They come to this Arduino Uno 8-9. Now the issue is, it must be TX connected to RX, so transmit to receive. But in this case, Akil soldered it such that TX goes to TX.
Alright.
And he needs to resolder it.
There was no signal going past, like, this joint, so I just added more solder, and now there's signal. So hopefully it works. Alright, so basically we had a problem with our ground. So this is the old wire here, and what was happening is there was no connection between this wire and any of the grounds on this. So the problem with this wire is there's like a lot of exposed stuff here, like, which shows how bad it was. And on the inside, there's literally just no wire anymore. We don't really see a wire there. So I replaced a new wire, and now there's actually a connection going to each ground. So we're hoping that might fix our problem.
While Akil was still debugging his circuit board, I turned my attention to LiDAR. LiDAR is a way of measuring distance to a point using lasers. Combined with a spinning motor, this allowed you to quickly get a 2D map of your surroundings. We're suspecting that this LiDAR board is broken, and if it is, that's not good. So it's spinning with the computer, which means that something is wrong with the Arduino. Even when we fixed all the electronics for LiDAR, we realized that our computers were actually too slow to record all of the points surrounding the LiDAR. In one full rotation, we would actually only get 3 random points, and of the 3, 2 of them will be pointing to the inside of the robot, meaning they were not usable. This left only 1 point, and this 1 point was probably pointed in some random direction, and it missed some obstacles sitting off to the side. As a result, we decided to drop the LiDAR until the near future.
Alright.
So, the GPS was sending us some corrupt data, and it turns out it was this one wire on the back of the perf board that it cut through the rubber insulation of another wire, so they were actually connecting when they weren't supposed to. Akil fixed that, so now we're just making sure that all works, and that's literally all we did today. So we are proceeding with the Arduino Mega Initiative. Arduino Mega Initiative, or AMI for short, is a complete redesign of our electronics board. We are extremely hesitant to implement this change because of the amount of work that it'll take me, Akil, to implement. Previously, we have been using SPI and I2C, 2 very fast communication protocols. However, there was an issue where if you put 2 wires close to each other, there would be cross interference. This meant that I would have corrupt data for the entire run. We decided to switch to another communication protocol called UART. This communication protocol was far more robust, and this cross interference was not an issue. This also meant that we could switch from 4 Arduino microcontrollers to only 1 Arduino board.
2 weeks later.
After we finished the AMI, all of our connection issues were resolved. We turned our attention to self-driving. While we did do our research in this topic, we really did not know how to make a robot self-drive. So we reached out to Yang Hua, who works at Waymo, Google's self-driving project. We figured that he had some pointers for us. After spending 3 hours on the whiteboard, we came up with a plan for the next couple months. Yusha's job was to create a path for our robot to follow. My job was to actually follow that path.
So what is STC? In its very essence, STC is a path planner. This algorithm gives the robot's navigation system a set of points to hit in a very specific order, and as a result, the robot covers the entire park while avoiding obstacles. So, now to briefly dive into the details of STC. The first thing we do is to define each square foot as either an obstacle or non-obstacle. We then generate a set of valid nodes based on this new map. From here, we run a graph traversal algorithm to traverse the nodes and create a guide of connections between nodes. From here, we can construct our final path to follow.
So here with me is a NavX IMU, and as you can see from the screen here, this can detect any movement and rotation from this NavX board. So for example, if I tilt this up, then it tilts up. If I tilt down, it tilts down. I can turn it, and then I can like spin it, roll. It's really cool. So we were working on trying to get data from the NavX onto the RoboRio via USB, and then trying to display it onto our console on the computer. So we just spent 30 minutes trying to do that. We're not even messing with the data, we're just trying to get the data. A technology that we implemented was called RTK GPS. RTK stands for real-time kinematic, and with GPS, this can get the precision of the GPS down to 1 centimeter. There's a couple of issues, one of them being that we only get a signal once a second, which means that we have to estimate the rest of the time. Another issue was that it required a base station at most 6 miles away from us. Luckily that there were some base stations around, so it was not a problem. So today, we marked a point which we are trying to hit. When I push down on the switch, then this thing will then turn on, and then it will turn to face the direction of the point and go in that direction like this until it reaches, and it'll stop. Okay, here we go. Go. Okay, yeah, no, this cut. Truth. Cut.
So what was the issue, Chris?
It thinks that we're like, oh! Okay, so basically what happened was I set a range in which that point would be considered arrived, and theoretically it should have been half a foot, but I think it's a bit bigger than that.
So it thinks you arrived.
It thinks we've arrived. Come on. So after it's correcting itself. It's correcting. It's actually working! Oh my god, first try! It's turning. Wait, hold up. No, you're so close. You're so close! Actually, I know what the issue is. Okay, I know what the issue is. Okay. I think my code is working. The reason why this thing is like having hard to discover the location is right now it doesn't have connection to the RTK technology, so it probably doesn't know its exact location. So it's kind of gauging where it is. The fact that it like got it first try though was kind of insane. I consider this a success. After days of debugging, the robot finally started driving straight.
Close. It's getting close. Alright, now I overshot. Oh, it just overshot again.
Alright. we ran into this very peculiar problem.
Okay, so right now, it's basically trying to turn in two directions at the same time. So first it tries to turn to the right, and then realizes, oh shoot, I need to turn to the left. And it says, oh shoot, I need to turn to the right. The cause of this is because a lot of the equipment we're working with that we haven't fixed yet is working on a 180 to negative 180 system. So what's happening right now is if this was 0, then it will turn to 180 degrees. And once it hit 180 degrees, the next degree over is not 181, but it's negative 179 degrees. And that's the issue, because then you have this huge gap that almost none of my code knows how to account for. So then it will be turning in both directions at the same time. It's kind of a big issue when you fix it.
Okay, so this is our first time doing a multi-node test. So the goal of this test is going to be to start here, calibrate it to north. We're going to drive to this point first. Once it reaches this point, it's going to know to switch to this point. This is the next point it needs to hit. Once it hits here, and the last point it needs to hit is this one. And then once it hits this, it's going to stop. Okay, and this should happen relatively fast, not like go jerk, and stuff like that. It should be somewhat smooth, hopefully pretty fast. So, yeah. Oh yeah, this is the second point, my bad. This is the second point, okay? Just so you guys know. For the record, this was the second point. We're not just like missing it on purpose. This was the second point.
I think we're done, Chris. I really think we are. You're not getting any closer.
No, it's fine. It just needs to make another 180-degree turn.
Did it arrive?
Let's go!
Did it arrive?
Yeah, I did. It arrived. As shown by the last run, we started trying to get more data from our tests. This involved hooking up a video to an output console. This meant that hopefully we can pinpoint the part where our robot started doing stuff weirdly and then find on the output console what our robot was thinking. However, we printed a lot of stuff to the console and the console started lagging, falling behind of the video, so it made it hard to pinpoint these problems. However, we still got some information out of this process, though not as much as we liked. Satisfied with our 3-point test, we moved on to the next step.
Okay.
So this is test number 1 with Gawala's spanning tree algorithm and my path handler. Ready? Okay. Let's go with
This is like such a chaotic first test. What is it doing?
We're running over the obstacle.
Well, I know what's going on actually. It's because it only thinks, never mind. See what it's done.
This is attempt 2. Let's hope it goes better than the last time. We learned from attempt 1 that we had screwed up data, so we plotted on Desmos, and we saw that it was a deformed triangle with screwed up stuff behind us. Anyways, it should be fine now. So we're gonna commence test 2. Chris, gun the motors. The viewers are waiting for this.
We clearly still had issues trying to cover STC paths with hundreds of nodes. Ayush optimized his code, now dropping the amount of nodes to only tens, And I started working on a calibration function to hopefully keep our measurement systems accurate. So right now, I am testing the calibrate function, and what we're going to be doing is from here, let it drive by itself straight for like probably 3 seconds, 5 seconds to like around here, and basically take the GPS location of its start and end and calculate which direction it is facing and add that to a gyroscope on the robot that may currently think that north is like this way, but then by doing this calibrate function, it should hopefully correct it so that it knows north exactly where it is. So, yeah, here we go. That's it. Okay. Hopefully it works first try.
One eternity later.
Okay, so after like a month, we finally got calibration to work. And turns out the issue was just this really small thing about unit conversion, so really annoying, man. But anyways, so tonight, we are trying to test Gaywalla's spanning tree algorithm along with our calibration code. The previous test, when we forgot to put in calibration, after like the first 5 nodes, it started breaking down because the yaw drift was getting too high. So we're hoping to correct for that with our calibrate and hopefully can make it through the entire run. And here we go.
After doing some research, we found a way to extract logs from our robot. This meant that we could generate a map to see what our robot was doing. This is what it looks like. The gray dots represent GPS signals, and the orange dots represents the times where my robot had to estimate where it was going. Clearly, as seen from this graph, it's a little bit off, and our robot just didn't seem to know where it was going. The issue seemed to stem from the NavX.
2 weeks later.
We have just discovered the root of all of our calibration issues and why we weren't following the path properly. We theorized that if the IMU was actually offset from the center of the robot, the dead center of the robot, then we'd get an offset every time we tried to turn a long way. So we did 3 360-degree turns, and we were off by
Like 90
degrees,
almost, actually.
yeah.
A bit more than 90.
And then we turned 3 full circles back, and we're back at 0. So
Yeah.
no yaw drift, it's just because the yaw's off-center.
Yeah. After a call to Akil, we were eager to test. However, the weather said otherwise. A rainstorm hit us, but we did not let that stop us. We bought a steel roof for our robot, which allowed us to still get GPS signal, and we covered the rest of the robot in green saran wrap. Even though we had all the data we needed to prove that the NavX was an issue, no matter how we positioned it, it was still the same outcome. Stumped, we reached out to Yanghua for some more helpful advice, and together we figured out a software fix to this problem. We tested again, hoping that this will be the last time we ever see of this problem.
This is the even bigger moment of truth. Is that a 90?
Yep.
The moment of truth?
We are a 90! Yeah! We did some more test runs, and the results were astounding. Confident in our work, we decided to go to the park and do a field run. While doing some turns in the park, we realized that our robot was actually digging up the grass, leaving dirt in its wake. So we went and bought some wheels that were smoother and had less grip on the ground.
Hello. Today we are at Panama Park again to show. This is our test case. We clearly have an athletic field closed sign just in the middle of our testing spot, so we have to go around it now. It's a huge feat, I know, but we're gonna do it today, guys. This is our first take. It's gonna be our only take. A couple new things. So far, we've only been testing with the computer off of the robot. Now it's gonna be on the robot, so debugging is much harder. Another point is that we are running on cellular data, so if anything cuts out, we are screwed. And absolutely screwed. Yeah.
Another issue we faced was that our local base station was down, which meant that we had to connect to one a little bit farther away. We hope that this would not disrupt the GPS connection, because if we lost fix during the run, then our robot would most likely not know where to go.
Meanwhile,
You can see the overall graph looks extremely good. With this solid final run, we mark the end of Phase 2. Thank you for all the support that I received while building this robot, and thank you to my teammates Ayush and Akil for sticking with this project for so long. Like and subscribe, and I'll see you in the next video.